Okay, this is 2018's breadth paper, which was used as the baseline test for the return of the year 13s. Question number 27, part A. Radio waves and X-rays are both electromagnetic waves. State one difference between radio waves and X-rays. State just means say it, no need to explain, no need to describe. So you can say a multitude of answers here: wavelength, frequency, photon energy, and many others too. But I would probably pick one and then sort of show the link between radio waves and X-rays. So I would probably write the wavelength of radio waves is much longer than the wavelength of X-rays. For part B, there is a star with a radius. The total power output of electromagnetic radiation from its surface is this power. The average wavelength of that electromagnetic radiation is 5 × 10⁻⁷ meters. So we've got a radius, a power, and a wavelength. Show that the surface intensity of the radiation from this star is this number here, 1.1 × 10⁸ watts per square meter. Now, the important word in this particular question is show that. Show. And it actually gives you the numerical answer. So what you need to do is clearly show that you understand where this number comes from. Clearly show the examiner by writing here in a way that shows them that you understand where this number comes from. What you can't do is just play around with some numbers in some kind of willy-nilly fashion where there's little to no chance of anyone following what you're trying to achieve, and then just at the end just put equals 1.1 × 10⁸ and then expect to get these marks. That's not the way that it works. You have to show that you understand what's going on, what the physics is behind the generation of this number. So with that in mind, let's start with the equation for intensity, which is power divided by area. The area in this case is going to be the area of a sphere with that particular radius there. So the area of a sphere is 4πr². I like to use arrows to show that I'm going to substitute this equation for the area of a sphere into this equation for intensity. And then I'm going to rewrite the equation, I equals P over, and then 4πr². That's my area of a sphere there, surface area of a sphere. And then, crucially, I'm going to chuck in all the numbers from the question. So 2.7 × 10⁻², that's the power given in the question, divided by 4πr², and r given in the question, 1.4 × 10⁹ meters. And then I'm going to plug that in on my calculator, and I will always do this feature at the end as well. If it's a show that style question, is I'll write the answer to several significant figures. So I've done 1, 2, 3, 4, 5, 6 significant figures there. And then finally, so I've got my unrounded answer, I'll then round it to the appropriate 2 significant figures to show that it matches the answer that was given in the first place. And it's very clear in this the workings that I've put down here, that I understand what's going on in order to generate that answer there. Make sure that you lay out your workings in a way that also shows that you understand what's going on. For part 2, calculate the energy of a photon of wavelength 5.0 × 10⁻⁷. Here you can start with Planck's equation, E equals hf, and we're going to substitute in the wave equation, V equals f lambda. V, the velocity in this particular case, is going to be that of electromagnetic radiation, or the speed of light, so V equals c. I know this seems silly, but I just like to spell everything out for the examiner so that they can see that I know what I'm doing. So substitute that into here. Rearrange this equation now to make frequency the subject, so F equals c over lambda. This frequency now is going to be substituted into my Planck's equation, and I'm going to rewrite this equation now with this substitution included. E equals hc over lambda, a common expression. I'm pretty sure that this expression is actually included in the equation sheet itself. Now the next bit I'll always do this is I will always write out all the numbers I'm about to type in to my calculator. So Planck's constant, 6.63 times 10 to the minus 34, times the speed of light, 3.0 times 10 to the 8, divided by the wavelength given to me in the question, 5.0 times 10 to the minus 7. I do this because the mark scheme, if I were to type this into my calculator wrong, fat finger syndrome, and just get the wrong answer and type out the answer here, I know that I can still rescue one of these marks, because one of these marks in the mark scheme is for seeing these numbers written down in this fashion. So this is the way I always secure myself against fat finger syndrome. Without doing this line of working here, and I accidentally do the wrong answer, I could lose both marks. So typing this onto the calculator, I can get this number here, 3.978. I've done 4 significant figures here, times 10 to the minus 19 joules. Before I write my answer on this dotted line, I'm going to make sure that I give my answer to the appropriate number of significant figures. And that's going to be 2, because the wavelength that's given to me in the question is to 2 significant figures. So I have to write my answer also to 2 significant figures. And in this case, that would be 4.0 times 10 to the minus 19. Many students are writing more significant figures than they can justify, and in some cases that can lose you a mark. Part 3, this is a good question. Estimate the total number of photons emitted per second from the surface of this star. Now, most of the students did struggle to get the right answer here. It could be that you've run out of time, or it could be that it's just a little bit of a tricky question. So, what I'm looking for is the number of photons emitted per second, a number of photons per second. So I'm going to start by writing the definition of power. Power equals energy divided by time. The energy in this case is going to be delivered in a number of individual photons. So that energy is going to be delivered in an integer number of individual photon energy packets. So hc over lambda is the energy of one photon, and I've got a number of those to supply the energy per second to create that power in the question. So if I make that substitution, put a little arrow to show where my substitution is going, rewrite the equation, P equals nhc over lambda t, and I'm just going to highlight this n and this t that are separated by this dividing line. So that's a number of photons, slash or divide or per, a number of photons per second. So this red bit here, n/t, is the number of photons per second. So what I would like to do now is rearrange this equation to make the number of photons per second the subject. So n divided by t, the number of photons per second, equals power times wavelength divided by hc. And then I'm just going to plug in the numbers from the question. Always show this line in your working. Always do this. So I've got power 2.7 times 10 to the 27, lambda 5.0 times 10 to the minus 7, divided by Planck's constant and the speed of light. So the unrounded answer to many significant figures is going to be 6.7873 times 10 to the 45 photons per second. But I now need to make sure that I write my answer on this dotted line to the appropriate number of significant figures. And you can see that I've got 2 sig figs, 2 sig figs, 3 sig figs, 2 sig figs. So my limiting factor is 2 sig figs. I'm going to make sure that I write my answer to 2 significant figures, which in this case is going to be 6.8 times 10 to the 45 photons per second.